So let us consider an example of fixed beam. So the question is like this: a fixed beam of span L is subjected to a central point load, W as shown. Analyze the fixed beam using consistent deformation method and draw shear force diagram, bending moment diagram, and elastic curve. So there is a fixed beam of span L which is subjected to a central point load. We are supposed to analyze that and draw the shear force diagram, bending moment diagram, and elastic curve. So let us say this is a fixed beam whose span is L and there is a central point load W. Okay, so this distance will be L by 2 and the remaining distance will be L by 2. So let us say this point is A, this point is B, and this point is C. Now we know in fixed beams we have two extra unknowns, and to solve we need two compatibility equations. The first compatibility equation is given as theta due to loads plus theta due to redundants is equal to 0, and theta is equal to area of BMD divided by EI. And the second compatibility equation is deflection due to loads plus deflection due to redundants is equal to sinking or rising of supports, and deflection can be written as area of BMD divided by EI multiplied by centroidal distance. So here the first step is we will have to choose the redundants. So I will choose the redundants as RB, or you can say VB, and the moment MB. I know at a fixed support there will be a vertical reaction and there will be a moment, so I'm choosing these two reactions as the redundants. The direction of the redundants is up to you. You can choose any direction. And now after choosing the redundants, I can split the beam into three beams. One is cantilever with point load W. This is L by 2. This is L by 2. Point A, point B, point C. One more is cantilever with redundant RB. This is L. And one more is cantilever with redundant MB. This is point A, point B, and point C. So I'm splitting the entire fixed beam into three simpler beams. And for these beams, I have to draw the bending moment diagrams now. So for cantilever with point load, I will get a hogging BMD with triangular variation like this. And here the bending moment will be W into L by 2. This span is L by 2 and L by 2. This is point A, point B, and point C. And for cantilever with RB, we will get a sagging bending moment with triangular variation, and this bending moment will be RB into L, which will be positive, and this span is L. And for cantilever with end moment, we will get a rectangular BMD, and the bending moment is constant throughout the beam, which will be MB, and it will be hogging in nature. So this is negative, and this will be MB, this will be MB, and the span is L. So these are my bending moment diagrams for the beams due to loading and beams due to redundants. So now the centroidal distance has to be taken from the centroid till the redundants for each case. So these will be the distances x bar, right? So now we can apply our compatibility equation 1 and compatibility equation 2. So if I apply compatibility equation 1, so I have to apply it for each beam. So that is area of BMD divided by EI. So here area of BMD will be, it is negative, so it is minus half into base is L by 2, height is WL by 2, half into base into height divided by EI is not mentioned specifically in the example. So let us take EI is constant, and for the second BMD it is positive, so it will be plus area of BMD is half into base into height, that is half into L into RB into L divided by EI, and here it is hogging BMD, so it is minus area of BMD will be L into MB, so that is minus MB into L, and this is equated to 0. If I simplify this equation, I will get RB into L square by 2 minus MB into L is equal to WL square by 8. So here we have two unknowns in the form of redundants, that is RB and MB. So I'm keeping these two terms on one side and I'm sending the other term to the right hand side. So I get this equation. So I will say this is equation 1. Now applying second compatibility equation, that is area of BMD into X bar for all the BMDs, we get another equation. So here area of BMD will be half base into height, and the centroidal distance is 2/3 of L by 2 plus L by 2. And for this case, it will be half base into height, area of BMD, and the centroidal distance will be 2/3 of L. And for this BMD, area will be L into MB, and the centroidal distance will be L by 2. So if I apply that in my second compatibility equation, I will get minus half into base into height divided by EI multiplied by 2/3 of L by 2 plus L by 2. That is for the first BMD. Second BMD is sagging, so it is plus. Area is half into base into height divided by EI, and the centroidal distance is 2/3 of L. And for third BMD, it is rectangle, so area will be MB into L divided by EI, and the centroidal distance will be L by 2. This is equal to total settlement of supports. So because there is no settlement of supports mentioned in the problem, you can take this as 0. Now again here you can note there are two unknowns. One is RB and one more is MB. So we can simplify this equation as RB L cube by 3 minus MB L square divided by 2 is equal to 5W L cube divided by 48. So this is my second equation. So now we have two equations with two unknowns, that is RB and MB. So if we solve equation 1 and 2, then we can determine the values of RB and MB. So here, to solve these two equations, you can do equation 1 multiplied by L by 2 minus equation 2. So this will give us equation 1 into L by 2, that will be RB L cube by 4 minus MB L square by 2 is equal to W L cube divided by 16. And minus equation 2 will be minus RB L cube by 3 plus MB L square by 2 is equal to minus 5W L cube divided by 48. So if we solve these two equations, this term will get cancelled and we will be left with minus RB L cube divided by 12 is equal to minus WL cube by 24. So here the only unknown is RB, so you can solve for RB, and RB is calculated as W by 2. And once you have the value of RB, you can substitute it back either in equation 1 or equation 2, and you can calculate the value of MB. So let us substitute RB in equation 1. So we will get substituting RB is equal to W by 2 in equation 1, we will get W by 2 into L square by 2 minus MB into L is equal to WL square by 8 Now here the only unknown is MB, so we can write this as WL square by 4 minus WL square by 8 is equal to MB into L. So if we simplify this, we will calculate MB and the value is WL by 8. So now using equation 1 and 2, we have solved them and we have determined the value of RB and we have determined the value of MB. So here the fixed beam is like this. This is point A, point B with central point load W. This is L by 2, this is L by 2. So here at B, we have RB, which is W by 2. So we have an upward reaction here, RB, which is W by 2. And the moment is WL by 2. It is positive. So what it means is we have considered clockwise direction here and we have got a positive value. So the assumed direction is correct. So here we have MB, which is WL by 8. Now we have two more unknowns, that is reaction at A, and also we can calculate moments at various points. And we also have moment here MA, whose direction we don't know. So now let us calculate reactions. So if I consider sum of all vertical forces is equal to 0, then I will get RA plus RB, that is W by 2, is equal to minus W, that is downward W, so it is W. That is upward forces is equal to downward forces. So from here we can write RA is equal to W minus W by 2, that will be W by 2. This is the reaction at A. So now we know RA is also equal to W by 2. So now you can draw the shear force diagram. You know RA and RB. So I can draw shear force diagram. So at point A, there is upward force W by 2. So this has to go up by W by 2. From A to B, there is no, this point is C. From A to C, there is no load, so it will be uniform. At C, there is a downward load of W. So it will be W by 2 minus W, that is minus W by 2. From C to B, there is no load, so it is uniform. And at point B, there is an upward force of W by 2. So this is minus W by 2 plus W by 2, you get 0. This is positive, this is negative. This is the shear force diagram. Now to draw the bending moment diagram, you have to calculate bending moments at various points. So say calculation of bending moments at various points. So here we already know that MB is equal to WL by 8, and if you consider sagging as positive, here MB is a hogging moment, so this will be minus WL by 8, and moment at C will be at this point. Consider a section at C and consider right hand side. If I consider right hand side, so this will be minus WL by 8 due to this moment MB, because it is hogging, and RB into L by 2, so this is sagging, so it will be plus RB, that is W by 2 into L by 2. So moment at C will be WL by 8, and moment at A will be, if I consider right hand side, so imagine a section at A, and on the right hand side you're taking the moments. So due to MB, it is hogging WL by 8, so minus WL by 8, and due to RB, it is sagging, so it will be RB into L, sagging RB into L, and due to this point load, it will be W into L by 2, which is hogging, so it is minus W into L by 2. So this is calculated as minus WL by 8. So what it means is, at A, the moment is hogging WL by 8. So this moment is hogging, and the value is WL by 8. So hogging WL by 8, so it is minus WL by 8. So now we know moments at all the points. So you can draw the BMD. So this is your reference. So this is point A, point B, and point C. So at point B, it is minus WL by 8. So say somewhere here. And at point C, it is positive WL by 8. So say somewhere here, WL by 8. And moment at A is minus WL by 8. So here, this is WL by 8. And because it is only one single point load, you can join all these points by straight lines like this. So this is your BMD. This is negative, this is positive, this is negative. And you have 2 points of contraflexure here, so which can be calculated if required. And the elastic curve can be drawn like this. This is point A, point B, point C. So from point A up to this point, it is hogging. So this has to hog like this. From this point of contraflexure till here, it is sagging. So this has to sag till here. And from this point of contraflexure till point B, it is hogging again. So this has to hog. And these are your 2 points of contraflexures. So this is the elastic curve for the fixed beam with central point load. So I'll be solving some more examples in subsequent videos. Keep following.